All right, everybody. Yes, it is time. Okay. Try and not have the master golf on my iPhone playing whilst we lecture. All right. So today we are going to bridge to PDF. Did I upload the severe weather one? I think I okay. Thank you. Yeah. So here's where we're at. The shenanigans that we went through on Tuesday, all of this looking at electricity, which is just another way of looking at spin, right? It's the spin is the avenue that we go down to get to areas in the upper level. We cannot actually measure that convergence, but we can measure spin. So that's why we spend so much time looking at electricity and spin. So we went through all of that to look at how air moves through troughs and ridges, right? As it meanders through these troughs and ridges. And actually why it generates divergence and convergence. Right? It's generating divergence and convergence because of the changes in its relative vorticity imparted by curvature and changes in speed, okay? And also changes in the planetary vorticity, which increases, or what we now think about now that we've introduced the concept, Coriolis vorticity, right? The spin that's imparted by just simply moving across the surface of the planet. So that's where we're at. This morning, I want to use the divergence bit, and this morning's lecture is much more straightforward. First part, I'm going to use the divergence part to look at mid-latitude cyclones, okay? The major storm system that impacts us here across the lower 48. So we'll finish off the mid-latitudes by looking at the mid-latitude cyclones. I don't know, that should take 30 minutes, maybe a little less, something like that. Very straightforward. And then we'll go over to severe weather. Severe weather will be split into two parts. This morning, we'll just go through the broad synoptic ingredients. And you're already familiar with a lot of these terms, right? Like paper and so on, but we'll tie it all together in terms of ingredients. And then next week on Tuesday, we will unpack tornadoes specifically. And that is finally exciting. We've been waiting 11 weeks on that. 11 anymore. So that'll be tornadoes. And then we move into the climate side. Well, no, first we'll go to weather forecasting. Okay, that'll be next Thursday, and then we end the course on the climate side. We'll do natural climate change, anthropogenic forcing, and then we'll see where we are in terms of that final lecture. So there's a little glimmering light at the end of this meteorological tunnel. Hang in there, we're getting there. Okay. So we'll start with this diagram here, which just brings us back to this overriding concept, right? Probably are a bit tired now, but where air is converging at the surface, somewhere it must be diverging above, right? And vice versa. When it's converging in the upper levels, there must be divergence at the surface in order to maintain and conserve the overall momentum of the atmosphere, right? So that's what's going on. So let's just look at the right-hand side of this trough. So here's the trough axis. We've got a very simple cartoon here. We've got a low pressure at the surface with air spiraling in towards the low. As it rises, okay, we've gone through this many times now. You should be totally comfortable with this rising and cooling by expansion reaches its lifting condensation level. Heat's rising, bless you. We've got clouds developing. And then eventually, to keep all of that uplift going, we've got to have divergence in the upper levels, right? We're now at a point where we can say that this divergence here is generated not because the air is just simply piling up or going from 8 to 4 to 8-lane highways, but because vorticity is changing the convergence of mass and the divergence of mass. But on the right there, okay, there's a couple of important points, right? One is the upper level divergence, okay, must be greater than the low level convergence, right? In other words, you've got to have slightly more divergence going on a lot. You've got to have the vacuum cleaner taking more air out, and only by a little bit, okay, to remove mass from this column, right? If we've got a surface pressure, let's just say it's 1,000 millibars over here. If we want this to strengthen, in other words, if we want this load to deepen, to go to 999, 988, and so on, right? We've got to remove more mass. There's got to be a net loss of mass out of that column of air. So the pressure at the surface begins to drop, right? That should make sense, okay? Right? So the divergence must be greater than the lower level convergence in order for the surface pressure to drop. I think probably intuitively that makes sense. But this middle bullet point here raises an interesting concept, I think, and that is that rising air is cooling, right? Rising air cools by expansion. And cooling air slowly starts increasing its density. That's the definition of cold air. Cold, dense air, right? So that rising air is gradually increasing its density as it's cooling. And if you're increasing the density of the air, you're increasing the weight of the air in that column. So the divergence must be greater to overcome that as well. It's not just simply that the divergence has to be greater than the low level convergence to remove mass. It's got to also offset any kind of changes in density in that column. That may seem like a super small point and we could have just left it out, but I put it in. Okay. All righty. So having said all that, how does this play out in terms of these major storm systems that impact us, right? So we're going to look, so the major storm system here is the mid-latitude cyclone. So the mid-latitude cyclone is the relay switch. So here's the low pressure here, okay? And it is the relay switch that allows warm air, the air is circling around that, okay? It allows the warm air on the southern and eastern flanks to be advected. Advection is the horizontal movement of heat, right? So if I'm standing in the center of that load, and I've got the Gulf behind me, Houston down there, and here's the Great Plains, right? As I start turning inwards, it allows that warm air to move north, and it helps advect that cold air back out to the south. That's why these mid-latitude cyclones are referred to as these atmospheric switches. And there's a number of recognizable features here, right? So the mid-latitude cyclone would have a low, right? Not all lows are mid-latitude cyclone. So the mid-latitude cyclone is the kind of inclusive name for the storm system. But it's a cyclonic storm with a distinctive cold front, right? A warm front. And if it's at a stage where it's starting to occlude, then it's got this little purple front. And I'm going to explain that as well. Point here is the precipitation that is associated with these mid-latitude cyclones follows a very predictable pattern, right? You get storms, and you can see that on this little diagram that I've used here. This is heavy rain, flash, severe thunderstorms. This all occurs in association with the cold front and the warm front. Remember, I'm going to talk a little bit more about how this model develops. This warm front is retreating in that direction. The warm front isn't pushing into the cool air here, right? It's retreating. As that cool air retreats, it creates the warm front. That whole system the low, the fronts, rainfall, that's what we refer to as a mid-latitude cyclone. Right? It's the major storm producing system here in the mid-latitudes, especially in the lower 48s. When these systems develop off the eastern seaboard here, and they develop out here, we call them nor'easters, right? Because all that air that's blowing around on the eastern flank is coming out of the north and the northeast. It's the same thing. So a nor'easter is just a mid-latitude cyclone for the eastern seaboard. Okay? This is typically what we see. So these are synoptic systems, large-scale systems. Okay, and you can see with the mid-latitude cyclone, the distinctive features are the frontal convergence. So thunderstorms, sometimes they're severe. We're going to examine that later when we look at the ingredients for severe. But generally speaking, we've got lines of storms. They can be squall lines if they're quite severe. Then we've got this massive rainfall as that air is riding up the warm front. It's much more widespread. Generally speaking, then we've got frozen precipitation directly around the back. The low would be right in the center over here. So large-scale cyclonic storm systems. Okay. Okay. So like, excuse me, like thunderstorms, mid-latitude cyclones go through a genesis and go through a set of cycles. This is really simple. This all came out in the 1920s and 1930s out of Norway, actually. Sometimes this is referred to as the Norwegian model of storm systems, because some bizarre reason there was a group of meteorologists all working on weather systems in the 1930s. And this became actually really important when it came down to World War II, right? And you were doing things like bombing runs, and you launched D-Day or not. All of that was dependent on the ability to forecast, and the best forecasters were the Norwegian physicists. And so how do mid-latitude cyclones form? They almost always form along a stationary front initially. So just a boundary where there's warm air to the south and cold air to the north. Some kind of stationary boundary, right? Just with differential air masses. And you see that across the Midwest. Warm maritime tropical behind me, you know, the continental polar in front, okay? This here shows that the winds are blowing parallel to the front. They don't have to be absolutely parallel to the front, but it's just simply a bound that's not doing much. Okay? That's the initial condition. And then the initiation and this process, because we have to have a fancy name, it's called cyclogenesis. So cyclogenesis is the process that forms these mid-latitude cyclones. Okay? So the beginning stage of cyclogenesis or mid-latitude cyclones is a kink develops in that stationary front, right? You've got to have some little wave or kink that develops in the stationary front, okay? Where, this is not controlled by the surface. This is controlled by the upper levels, right? In the upper level jet stream, or somewhere in the region of 5 to 300 millibars where the winds. Okay, so if the center of the floor here, let's say this is a stationary front, and we've got warm air to the side and cold air to this side, right? The way in which a kink develops is a little wave or an upper level low or a trough comes over that stationary front. And it doesn't have to be a big, deep trough, just a little kink, just enough to get the surface to go, uh-oh, you feel a little bit of divergence above, and it starts beginning to turn in on itself, right? So this front develops this little kink where this wave in the upper levels is developing. And the stationary front then begins to change from a stationary front into a developing cold front moving this way and a warm front moving that. Does it make sense? It's just the initiation phase, okay, of cyclogenesis. So that's the beginning stage. And so it develops, right? It begins to intensify, and I'll show you why it begins to intensify just at the end, right? But it begins to intensify as that upper level disturbance moves over it, and the fronts become better organized, right? So you start getting cold air advection in this direction and warm air advection in that direction. Okay. And what you start seeing then is a much sharper, distinctive change in temperatures and wind directions as that frontal system develops. Right? This is all part of this term called cyclogenesis. But it all starts with some upper level disturbance coming over and causing that surface system, that surface boundary to go, I think I'm going to start turning in on myself. And how does that start? It's the trough with the upper level divergence on the eastern plane that provides the uplift, and the surface goes, oh cool, I think I'll start turning in on myself. So that's the intensification stage. In the mature stage of a mid-latitude cyclone, right, it develops into a full, true, mature wave cyclone. Sometimes it's referred to as a comma cyclone. So here's the low, and this looks like a big comma, right? And in the mature stage, the mature stage is signaled really by the development of what is called an occluded front, right? So an occluded front, because the cold air is moving in more quickly than the warm. So the cold air is being forced into the warm, and that warm air is retreating. Remember, the warm front isn't driving the system, right? So the cold air is moving in, the warm air is retreating, okay? And because the cold air is moving more quickly, it catches up to the warm air, right? It catches up to the warm front here. And that's when we get an occluded front. And basically all an occluded front is when the cold front catches up to the warm front and then lifts that warm air above the whole system. And that's where you get the purple line with the alternating triangles, okay? So that's the occluded front there, okay? And then it begins to die out, right? And this is known as the occluded phase or an occlusion, right? And basically what happens is the cold air, the cold front wraps around and completely catches up to the warm front, lifts all of that warm air above it. And now what you've got is cold air juxtaposed to cooler air, and the system runs out of energy. It doesn't have those very sharp temperature gradients across it. Okay? And it eventually dissipates and dies out until an upper level disturbance comes along and tries to find another little area. Oh, I think I'll cause some turning over here. Does that sort of make sense? That's all known as cyclogenesis, right? A stationary front that begins to turn in on itself, all driven by an upper level disturbance that comes over it, and then the system begins to feed in on itself. You may have heard of the term, so that's cyclogenesis. You may have heard of the term a bomb cyclone. You may see that much more likely in the winter time, right? And so a bomb cyclone is a specific term that you assign to a mid-latitude cyclone, but you have to drop the surface pressure 24 millibars in 24 hours. Right? So over a 24-hour period, the pressure drops by 24 millibars, basically a millibar per hour. That's technically a bomb cyclone. Okay, so when we look at cross sections then across a cold front at the surface and a warm front, this is very typical what they look like. And this is why the rainfall precipitation looks very different across cold fronts and warm fronts, right? So this is the surface cold front, and here is this dome of cold air. The cold fronts have much steeper boundaries, right? It's a big blob of cold air. And that's why it's just such an important forcing trigger mechanism to get air to go up very quickly over very short horizontal distances. So you might have heavy, warm, moist air sitting here over the south, and a cold front comes in, and that air can only do one thing, and that's go up, right? And that's why we have intense rainfall, thunderstorms, squall lines, perhaps even severe storms along a cold front. Whereas with a warm front, that rainfall is much more spread out, right? We don't have squall lines or anything associated with warm fronts because this warm front is retreating of the cold air retreats, and this is the gradient of the warm front. Much more gentle, right? So with cloud types along the warm front, you have this grade from you can get nimbostratus and then the altostratus and then the cirrostratus and the cirrus. I don't know if you remember when we talked about clouds, I said the cirrus and the cirrocumulus clouds are often, cirrostratus in particular, are often precursors of a storm coming in the next 24 to 48 hours, right? That's because the clouds here are associated with a warm front. The technical term for that is called overrunning. where those clouds are overrunning the warm front. Start seeing this nice gradation of different cloud types. With a cold front, you don't. Cold front, you see cumulus, cumulonimbus, nimbostratus, all over very short distances. That make sense? And I don't have an animation of this or a diagram of this. So this is a cold front, and that's a warm front over here along the surface. The occluded front would be when this cold front moves into the warm front here, pushes it in, and lifts all of this warm air above it. Then you would have the purple line on the surface, and the storm system would be in its 9 phases. And these are the 2 images I sent you on Saturday as part of my nerd alert, right? So yeah, this was Saturday. Here we are. So you can see here's the load, right? This is the precipitation associated with the cold front. The warm front was actually not, there was not a lot of rainfall here associated with, and then there's snow wrapping around the back end of continental polar air. And then this was the surface analysis. I know it's pretty small there. There's the low, there's the purple occluded front, there's the cold front moving in, there's the warm front. I don't know if you can see this, but look at the wind directions, right? All of the wind directions are out of the south here. This is known as the warm sector for obvious reasons. Yeah? And there is much colder behind, pressure starts increasing as that cold front moves. Cold front goes through, wind changes direction from south. You can see, I'll just point the paint here on where these arrows are all pointing. Yeah. Absolutely classic. So the wind shifts around from the south and southeast in the warm sector. Cold front comes through that, wind shifts around to the northwest. It's that cold air that's around the back of cooler air, depending on the year. Any questions on that? That make sense? Okay, good. All right. The final part of this, we're doing good now, okay, is this little concept. I want to get terribly bogged down in this, but it's just an important concept, and that concept is self-development. Okay, the surface load and the frontal systems, they're not isolated and acting independently of the atmosphere, right? They're like sticks in a stream. They're being driven by the overall flow in the atmosphere, and self-development is a positive feedback mechanism that happens, right, during cyclogenesis. It's how mid-latitude cyclones develop, this notion of self-development. Think of it as a bunch of dominoes, right? So we've lined up all these dominoes along a stationary front. And something has to go first. You've got to push that first domino over. And the first domino over is this little kink that we talked about to get the system to start turning. I don't know if this works. Let's see if it does. I've tried to draw this looking. We've got the surface on the right here, and I've kept it super simple. So here's a low, there's cold front, there's a warm front. The black lines are the isobars. We don't have numbers on here to make it complicated, but this would probably be like 996. These brown lines are temperature lines. Okay, so the temperature lines wrapping around the back of the solar system. So those are the isotones. Then looking down on the left-hand side is the 500 millibar surface. 5640, 5580. C is, I don't know what town that is. I should have looked it up. I just put a green blob there. That's somewhere in the middle of Alabama on both maps, right? So you can see here there's a trough here, right? Over here. There should be some sort of divergence going on here. And this is where the low is developing underneath the divergence. Does that sort of make sense? It's a classic setup, okay? So what is self-development, okay? So self-development starts with this little trough or kink in the 500 millibar surface approaching a stationary front, and it removes the mass, right? We've already said that from the model we drew. Stationary front, 500 millibar trough comes along, meanders like that over it, the divergence does that, and the surface goes, cool, I think I'll start going up, and it starts rotating ever so gently along that front. So you're removing mass, okay, right here in the center of the load. Okay, cool. And then, as this little fledgling load starts circulating, you start getting the cold air advection around the back and the warm air advection in the front. Remember, advection again is the horizontal transfer of heat. Right? Convection is the vertical transfer of heat. So you've got warm and cold air advection. You've got warm air advection doing that, and cold air advection doing that. Does that make sense? Okay. So those are the initial set of dominoes. Now, as I click to the next one, look at the relationship that's going on here between the trough and the low. As that cold air advection starts, so let's say I'm standing in the middle of the low here, right? And you guys are in the cold sector, and the cold air advection is coming in here, and the warm air is moving up to you guys over here, right? That cold air advection brings in a shorter column of cold air. Remember our friends called column of warm air, shorter column of cold air? So that shorter, the cold air, which you guys are that are now moving in towards me at the center of the low, that lowers the 500 millibar trough. It lowers the surface. Okay, that's the important second domino in all of this. The cold and warm air advection that's going on lowers that trough, and it steepens the trough, right? So this infusion of cold air that's starting to wrap around the back here strengthens the upper level trough. There's a sort of backwards and forwards going on between the surface and the upper levels. I'll just go back 1 second here. So here we've got fairly gentle trough and cold air advection. As that cold air advection comes in, it lowers the trough, right? It steepens and strengthens that trough. And if the trough is strengthening over here, what do you think is happening to the convergence on this side and the divergence on this side? The divergence here is going, you think it's going up or down as the trough steepens? Going up, right? So as the trough gets more bent, remember that if it's zonal, you don't have much divergence and convergence. A big deep trough, very strong convergence and very strong divergence. So as that cold air comes in, it lowers the 500 millibar height. And the deeper the trough, the higher the vorticity, right? And the higher the vorticity, the greater the divergence. And the greater the divergence, the surface load goes, awesome, I think I'll strengthen, right? And so that is the self-development process that goes on, all right? Increased divergence on the eastern side, it strengthens the load, you steepen the pressure gradients, you get faster winds. The faster winds increase the advection of cold and warm air. The increased advection of cold air deepens the trough, and the dominoes start rolling, right? It's a positive feedback mechanism between, as you start the low developing to the cold and warm air advection, lowering the trough, increasing the divergence, steepening the cold air advection, lowering the trough. It goes on until it occludes itself. Question?
Is this a part of the initiation or?
Exactly. Yeah, this is just another way to look at the initiation, the mature stage, the developing, and the occlusion, right? I wanted to try and end with this just to make the point that it is a positive feedback mechanism. It's not kind of acting independently of anything else, right? It's all part of cyclogenesis. Yeah. I probably won't ask you something on self-development, but I just wanted you to be aware. When you see a big mid-latitude cyclone moving across the US, there is this self-development between the cold and warm air advection surface, steepening of the trough in the upper levels, and that increases the advection. So it goes on and on and on. Questions? So that's a mid-latitude cycle. So if I was to hypothetically give you an exam question, maybe, and the exam question had two lows, like this, okay? And the one low, this one here is Hurricane Audrey. And this one is an unnamed mid-latitude cyclone. Both of them have big low pressures with counterclockwise air circling in towards the center. If I was to give you a question that said, discuss the similarities and the major differences between these two types of cyclones, because they're both cyclones, right? This is a cyclone. A cyclone is counterclockwise flow around the center of a low. And in the Indian Ocean, we call these tropical cyclones. This is a mid-latitude cyclone. I would probably, if I was to take an over-under on whether I would ask a question like that, I would I put money on it. You're going to see a question because it's the two major storm systems in these two geographic regions, right? Tropical cyclones and mid-latitude cyclone. Describe, discuss, explain. What's the other one? Compare and contrast. Right? There's lots you can say about that in terms of where they get their energy from. One's latent heat, one's frontal temperature gradient, so on. Right? That makes sense? So that would be a nice little question. Okay. Any other questions? Any questions on? Makes sense. Good question. All right, let me just get rid of this and then we will change gears and get from Hannah's perspective, as my Texan wife would say, finally, we're going to get to severe weather. All right. Okay. So let's talk about severe weather here. This is one of the joys of teaching this course. Even after all these years in a place like Texas, especially at this time of year, right? So this is very relevant. Part of the reason why I actually teach with them finally in the spring. Is that we are right at the perfect time of year to talk about severe weather. Let's go. Again, we're going to strip this into the ingredients and then neighborhoods. Okay. So just a reminder, I've introduced you to this before. The term severe has very specific connotations in meteorology. A severe storm or a severe storm warning, a severe storm watch is only issued when one of these three things is either likely to occur or occurring, right? A tornado, and a tornado by definition means there's been ground contact. Okay? You can't just have rotation and call it a tornado. Anything that's rotating up there that hasn't touched the ground is generally referred to as a mesocyclone. Okay. Once it touches the ground, it's a tornado, or it's producing hailstones that are an inch in diameter. It used to be 3/4 of an inch. But a few years ago, the National Storm Center changed that. Or it's a storm that's generating straight line winds of greater than 57.5 miles an hour. No idea why they came up with 57.5. Probably right in the middle between the onset of a tropical storm and a hurricane. But straight line meaning horizontal, not rotation. So those are the three identifying characteristics of severe. Okay. And we happen to live in a part of the world where these ingredients that I'm going to talk about come together like pretty much like nowhere else. Okay. So this map here, it just shows the 10 deadliest tornadoes. This just is one specific type of severe system, obviously, tornadoes, but it's a nice map. There's a moderate risk and a high risk. Okay, so there's a couple of isolated areas along here, a frontal boundary. Here in the central part, that's actually the mountain kingdom of Lesotho. This is an area back in my home country where we do get some different air masses coming together. And then the Aussies have some risk over there. The tornado risk over here, and the deadliest one here, is actually associated with monsoon rains in Bangladesh. Okay, but nowhere else does it come together like where we are, the big purple blob. Okay, there's really a set of unique conditions, and it's not just the geography. Okay. But that's what we're going to take a look at. So, at a incredibly simple level, most people, I think, just think that we are vulnerable here in the plain states because we've got warm, moist air and cold, dry air. Clearly, it's not that simple. But that's the first part of this whole picture of severe weather where we live. Okay? The geography of this region, especially as we've got the Rockies over here, right? And we've got the high plains of Mexico over here. The southern plains geographically are open to maritime tropical air and cold continental polar air, cold dry stable air. That's one of the ingredients. That's one of the dominoes. This is the real reason in a bit more detail. Okay. So, and this map isn't to suggest that the dry line and the low pressure only form just above Emma's beloved Oklahoma here, this shifts to the east. You'll see the map of so-called Tornado Alley in just a second, and just how broad it is. Okay, there are actually multiple tornado alleys. But I like this one because from a sort of geographic perspective, these are the main ingredients that set up the plain states for severe weather. So one is warm, humid air, okay? And the second is cool, dry air, right, that meet around the low pressure. There's a very unique positioning of the jet stream. We're going to get to all that. The triple point is just where the warm front, the dry line, and the cold air meet. The tornadoes and severe weather isn't always associated with a dry line. Remember, a dry line, we'll show you that again in a bit more detail. Dry line is just a frontal boundary between moist maritime tropical air and dry continental air. Okay? But all of these ingredients come together at different times in the spring across the plain states, like nowhere else on the planet. The most significant storm system for severe weather, okay, is the supercell. So if you remember when we talked about thunderstorms, and we looked at various classifications, we looked at air mass thunderstorms, right? Thunderstorms that develop in broad, warm air masses. Or the other one was synoptically forced. Remember, thunderstorms that form along a frontal boundary. Severe weather almost always comes with synoptically forced systems, right? You very rarely find severe weather in large areas of just popcorn cumulus clouds. Okay? So these are generally synoptic systems. And the storm system that is most responsible for severe weather, whether it's tornadoes, hail, or straight line winds, is the supercell. Okay? The supercell is a large, massive single cell storm. Large single cell storm. Severe weather certainly occurs along squall lines, but the supercell is, and I don't know what the percentage is, my guess is it's probably something like close to 3/4, maybe more, of what certainly tornadoes occur with supercell storms. Okay, and a supercell storm is a cumulonimbus cloud, okay? The large anvil. The anvil is where the updrafts are pushing up against the tropopause and spreading out, right? So whenever you see an anvil, you know you've got convection through at least 30,000 feet. Very frequently, we've got an overshooting top, which actually is the core of this, the fastest updrafts, and beginning to puncture through the tropopause. You may or may not have a wall cloud. I'm going to come back and talk about wall clouds with tornadoes down here and so on, right? And the key distinction with a supercell, what is the fundamental difference between a supercell and a non-supercell storm is this. In a supercell storm, the updrafts, okay, the warm, moist air coming into the storm, and the downdrafts, right, all of the precipitation falling through the storm and the cold air coming through the storm, those are separated. And they're separated because the internal core of the supercell is tilted. And you can kind of see that here, right? In the core of the supercell here. It is tilted. The updrafts are tilted. And that is incredibly important because what that does is the downdrafts, the cold air, and that blue arrow isn't just coming in from the right here, it's coming in, wrapping around the storm. But all of those downdrafts, because the storm is tilted, do not cut the updraft off very easily. In other words, you can keep fueling the storm with warm, moist air moving in and cold air falling out without the downdrafts cutting off those drafts. If the updrafts and the downdrafts were not separated and the storm wasn't tilted, in other words, it was vertically upright, then eventually those updrafts would turn into downdrafts and the downdrafts would cut that storm off pretty quickly. And the reason why the entire storm is tilted is because of wind shear. We're going to talk about that as well in just a minute. Okay, so I like this little acronym. There are various ways of looking at this. You can see different ones online, but the acronym MIST always helps me remember what the what the 4 key ingredients for severe weather are. And there's a fifth, but we'll get to that. So these are the 4 big ones: moisture, instability, shear, and a trigger. Okay, moisture, instability, shear, and a trigger. You've got to have all 4 for severe weather to come into play. Okay, so let's look at these individually. So moisture. You do need a thick layer of warm, moist air. Okay, and preferably, it's not absolutely required because it just depends on the dynamics of the atmosphere. But preferably, that is a warm layer that has an inversion sitting atop of it. Okay. So in other words, if you look at the right, so this is just a visible satellite image showing lots of clouds and warm, moist. On the right here is a thermodiagram. This is a skew T. Okay. You don't have to worry about that, but it's very similar to your thermodiagram here. So these are the pressure levels here, and these are the mixing ratios here. And this is the temperature line, the red line, and this is the dew point. Okay. This situation in meteorology, I think it's on the screen. Yes, it is. It's often referred to as a loaded gun. Okay. This is like putting the shell into the gun and cocking it and waiting for something to happen. It's a loaded gun because we've got this inversion sitting here. So we've got moist air here. And I think this is an important point. When we talk about warm, moist air, I'm not insinuating that you have to have relative humidities of 90% at the surface, right? You don't. You've got to have moisture, and here the dew point would probably be 60 degrees Fahrenheit or 65 degrees Fahrenheit. So you can have a hot afternoon that might be 95, right? As long as you've got a high dew point, the relative humidity can only be 50%. Remember that whole discussion of why 90% and 90 degrees is not possible? So you've got to have low level moisture, okay? And you can see here that at the inversion, the relative humidity would be very close to 100%, right? The dew point and the temperature are pretty close to one another. And then the dew point collapses over to the left. Remember that for the exam and even your thermodiagram. When that dew point collapses over to the left, it means you've got an infusion of very dry air, okay? And the infusion of very dry air here almost always shows up as an inversion, okay? Again, you don't have to have an inversion, but it's the rule rather than the exception. With warm, moist air sitting over an inversion. And the kind of descriptive way to think about that is that the inversion acts as a lid, right? And so you can keep heating the bottom, put your lid on your rice, and it happens to me all the time, and I turn the stove on, and then I go and feed the dogs, and then there's rice everywhere. Eventually the thing convects and boils over. That lid keeps things cooking underneath it. And if the lid stays in place, you've got nothing. But if you can break the lid somehow, then you are off to the races. So the loaded gun is a warm, moist, lower atmosphere with an inversion sitting above it.
Is the green the air partial and the red the sounding?
No, good question. The green is the dew point, the red is the sounding. They're both the sounding, right? So the red is the temperature and the green is the dew point. Yeah, that's actually a really good question, Audrey, because if you were going to do the parcel, right, then the parcel would be following, these are the dry adiabats. Again, this is a skew diagram, but your parcel would start here. It would follow one of these dry adiabats, okay? It would get to the lifting condensation level here. On the skew diagram, the mixing ratios are all skewed. Don't worry about it. And then you would follow the dash line. So you would put a parcel on top of it. In this instance here, I'm actually really glad you asked that, because here it would follow, these are the dry adiabats here, right? So it would actually be, it would be kind of neutral-ish as it followed that. And then as soon as it got to here, you'd be toast. It would stop. It's underneath the inversion, right? So that's the sounding, but it's giving you both the temperature and the dew. That make sense? Okay. So that's the first one. And moisture. Gotta have it, right? Okay. Second, instability. High instability. You really want an unstable atmosphere, right? And an unstable atmosphere pretty much means a steep lapse rate. Okay, remember this? Go back to our instability diagrams here, right? And that's your dry adiabatic lapse rate, and that's your saturated adiabatic lapse rate. A steep lapse rate would be something like that. Rapidly changing temperature with height, right? Would be from the sounding, okay? Because here your parcel would be warmer, it would be much warmer, it would be unstable, right? More gentle lapse rate would be something like that. This would make it conditionally unstable. This would be the most stable environment that you could have with an inversion. So what you want is a steep lapse rate, right? You want a steep sound. In other words, you want it sloping as far to the left as you can. And what it really means, guys, in reality is conditional instability. Because if you've got warm, moist air below, then you're likely to have conditional instability. Okay? Yeah. So that's the second part, an unstable atmosphere. But MI, S, third one, shear. Yep. Strong vertical wind shear. So the wind shear, remember what wind shear is? It's a change in wind direction with height or speed with height. It can be either or, right? You can have winds doing this out of the southeast and winds doing that out of the southwest, and that's going to cause spinning and shear. Okay? You can have winds all blowing out of the same direction, with the top ones moving much more quickly. That is still going to set up horizontal spinning and shear. So you want strong vertical wind shear. So you may have, and I've tried to simplify this in these two soundings. So here's feet here. So we've got winds out of the south at 15, southwest at 10, southwest at 5, southeast at 5. Gentle winds, not much happening, right? That's just unorganized convection. Organized convection would be out of the southeast at 20, out of the southwest at 40, out of the southwest at 50, out of the southwest at 60, a much stronger change, a much greater change in the wind direction, but here in wind speed. So shearing is what gives the supercells the tilt. So wind shear is key, and then we've got to get T, ultimately the most important. Right? And the T is a trigger. Something's got to lift that air. Right? You can have warm, moist air, may or may not be unstable. You can have an inversion, awesome. So we've got the loaded gun. But if you don't have a trigger, you've got nothing, right? You've got to have something to get that air to go up. And by a trigger, a lot of people, and I think I've made this comment before, guys, a trigger, most people think it has to be something dramatic, right? Like it has to be a big, fat cold front that comes in. That'll do it. And we'll see why in a second. So that'll lift everything, whether it's stable or not. But more often than not, the lifting, the trigger, is actually really modest. Okay. And it's the, oh boy, here we go again. It's the upper level divergence on the eastern side of the trough that provides enough of the lift. Okay. So an upper level trough, the divergence here, the eastern flank, is almost always the trigger that we look for. Again, you can have a cold front come through, boom, that's awesome. But if you have any upper level trough, that divergence is enough to provide the trigger. Because really all you have to do is you've just got to break the inversion. And so these things all come together in this geographic region. This is why we sit in what is known as Tornado Alley, right? Is that here, so there's the Rockies over there, and here's the high plains of Mexico over here. Here are the southern plain states. And so here we've got the moisture, plenty of that. Okay. Low level jet, plenty of moisture. The instability is generally there in this moist air. The shearing is there because we have changes in wind, speed, and direction with height. We've got low level jets. We've generally got warm winds coming off the Mexican plateau. and we've got 500 millibar winds coming in on the eastern flanks of troughs. So the wind shear is almost always there. Okay. And the trigger is our old friend, the mid-latitude cyclone, that is associated with all of that. And this comes together nowhere else on the planet like it does our neck of the woods. So you might have, for example, 12-mile-an-hour winds coming in here, 37-mile-an-hour winds coming off the Mexican plateau, 60-mile-an-hour winds in the upper levels. You've got both directional and speed shear. And that sets up the environment that's really conducive to supercell storms. Okay, and we can see that over here. I'll come back and show you another diagram that's very similar to this in a second. So let's just take a look at so here's I've drawn a very simple diagram here. Here's the 300 millibar jet. Okay, this is where we get the upper level divergence on the eastern flank. Here's the cold front and the warm front. And the line of storms and the severe weather is sometimes right along the cold front, where it's a score line, but quite often it's out ahead of the cold front in that little low trough that sits out in front of the cold front. So don't be put off by that. But I really love this visible satellite image on the left here. Okay, so here's Kansas. There's a supercell right there. You can actually see the anvil in the striations. There's another one there. There's another one there, right? You can pick that up. You can see the shooting tops there. This is all associated. Here's actually the cold front back here, right? There's the cold front down there. And this is the trough out ahead of the cold. And it's that upper level divergence along the trough that's providing all of that necessary uplift in that particular instance. Okay, so let me just look at, I'll give you one scenario here. We'll see how we're doing on time. But this is a severe weather outbreak. And I'm not going to get into tornadoes here, although these are tornadoes. I always use this just as a case study to show how the ingredients come together. So this was April the 27th, 2011. Boy, I remember this. This was the deadliest outbreak of severe weather. 122 tornadoes in total, 62 in Alabama, 319 people died. And the strongest was an EF4/5. We're going to come back and look at what that means. That's the scale of the strength of the tornadoes. This isn't a line of thunderstorms. This is one storm just showing it through time, right? 21, 2200, 2300 in the morning. And on the right, you can see the entire outbreak. So it was a 4-day outbreak, okay, of different days. And reds are tornado warnings, right? These are different days of tornado warnings. Clearly, these storms are not operating in isolation. These are synoptically forced storms. It was absolutely an incredible outbreak. This is another map of it, of what it looked like. So the scale, I'll just introduce it to you. It used to be called the Fujita scale, Fujita. I'm going to come back and look at that on Tuesday. It's now called the EF scale, the enhanced Fujita scale. Again, we'll explain that a little later. Unlike hurricanes, hurricanes have the Saffir-Simpson scale, right? And you can go into a hurricane, fly a plane through it, you come out and you go, okay, the winds are 77 miles an hour. That's a category 1. You can't do that with a tornado, no matter what they say on the movie Twisted 1 and 2. Like you can't look at a radar image and go, oh, that's an EF3. You can only assess that after the fact with the damage. But the red is an EF4 and the purple is an EF5. These are catastrophic, right? These almost nothing can withstand these, but you can see how they form in these families along the frontal boundary through here. So here's how things set up on April the 27th. I know this is a little small here, but let's take a look at this. Here's the low, cold front, warm front, pressure here 993. Okay, so pretty significant. A yummy little dry line here. Okay, that was quite far east. And on the right here, I just want to highlight this. So here's Florida down here. This is the 70-degree dew point. So there's the 70-degree dew point, and these are the flow lines coming in off the Gulf, right? So that's the surface setup checked. Low level moisture, very high dew points. We've got the cold fronts and the dry lines. Absolutely perfect setup. Okay. This is the atmospheric sounding. right? So this is the sounding here. We've got green is temperature, light is dew point, there's pressure again, there's temperature, we don't have mixing ratios here, and here is the inversion. Look how close the temperature is to the dew points here. Right? This wasn't a particularly hot evening, it was late April. I don't think I've ever seen a sounding that has a dew point and a temperature almost lying on top of one another from the surface. So the surface temperature was 22, what's that, 40? Yeah, it's about 75 degrees in the evening, okay? And the dew points were 72. Relative humidity's off. What percentage? Someone give me a guess for the relative humidities right through this layer here.
Around,
Like if they were 92, yeah, good. Yeah, incredibly high relative humidity. So warm, moist air with our friendly inversion sitting right there. Okay. That inversion was the result of this continental tropical air coming in off the Mexican plateau. So this region right here, okay, is fundamentally important to tornado alert because it's at an elevation of 1.5 to 2 kilometers, okay, and it's dry air that just blows straight in over the Great Plains. And we often get the infusion of that dry air that sets up the inversions. Okay. Here's another look. Don't worry about the yellow plot. It's something else. It is a parcel, but don't worry about it. Here is temperature, inversion, warm air, collapse. This is not from that evening. I just want to show you a different look of what the inversion looked like. Okay. So here's a funky point, guys. And it's the trigger. And it's the lifting that doesn't have to be very vigorous. And why the lifting, when you have an inversion, causes such chaos. Okay. So let's say we've got humid air here. Okay. Let's say this is the lifting condensation level, 1.5 kilometers, whatever it is. Right. So air will rise and cool at 1 degree Celsius per kilometer. At the lifting condensation level, it's going to rise and cool at the saturated adiabatic lapse rate, right? 0.6 degrees per kilometer. And then let's say we've got a big inversion here. Here's the dry lid sitting on top of that. Does that make sense? Okay. How do you break the lid? Right? You can break the lid one of two ways. You can break it from below, or you can bulldoze it. Right? You can break it from below by keep heating this. Right? Keep heating the convection. Right? Put more and more moisture into condensed form and start basically eroding that lid from the bottom, right? Just turbulence in the lower layers as you heat that lower atmosphere. Does that make sense? Okay. And that turbulence will start slowly clawing its way around there. And what you're waiting for is one part of the lid to be broken. Okay. If it's eroded from below, that's what will happen. I think that happened about 3 weeks ago, 4 weeks ago, and 3 weeks ago we were supposed to have that severe weather outbreak and nothing happened. Because the lid what? We had another node out moment. We were watching and the lid stayed in place. All the heating was in place and they were just, and that's why we get severe storms that pop up so quickly and they can be so isolated, right? Is this, if it just breaks through the lid, then you will have what's known as explosive development. Okay? But here, the lifting, and this is why the divergence on the eastern end of a flame, this is why gentle lifting can be so important. Right? So think about this. Let's say we've got this situation right here. Let's see. And a trough comes over the top of this. So a trough comes in over here, and the divergence is over here, and this whole thing is lifted. Right? That makes sense? This whole thing is lifted. The lid is lifted, the inversion is lifted, the saturated air, the unsaturated air, it all goes, oh, nice, we've got a little trough above me. I think I'm going to start going up. I've got enough divergence above to start lifting them. Okay. What rate does this air cool at? Well, it keeps cooling at the 0.6 degrees per kilometer. See that? What rate does the air in the inversion cool at? This upper level trough, it's just lifting all of this. If this is going up, it's going to start cooling, right? Rising air cool. What rate does it cool at? If it is 1 degree per 100 meters. Everybody see that? If you bring a trough in over a situation like this, a loaded gun, and you lift the whole lot, the lower parts cool at the saturated rate, but the upper parts cool more quickly, right? And remember, ingredient number 2 is a steep lapse rate. If you can cool the upper levels more quickly, then you really are off to the races, right? So yes, you can erode a lid from the bottom, but the most devastating way to cause severe weather is to obviously to bring a cold front in, but you don't have to do that. You just bring an upper level trough in, lift the whole lot moderately, and your dry air is going to cool much more quickly than your warm air, almost twice as fast as your warm air. And so the moist air below is awesome. That's pretty unstable above me. And off you go to the races. Okay. And finally, something that you're familiar with. Okay. It all comes down. Once all of that happens, right? If you've got the moisture, the instability, the wind shear, the trigger mechanism, everything's in place. Okay. You've got to get your air to the level of free convection. Keep an eye out on that on your thermodiagram, the way that occurs, right? Because once you get your air parcel to the level of free convection, then it doesn't matter what's going on in terms of triggers and instabilities. You've got free convection through the atmosphere. Right? So the convective available potential energy. But first, you've got to get there. That's the key. You have to get there. And all throughout that is you've got to separate the gates. You've got to separate the updrafts from the downdrafts. Okay. And this shows a vertical profile of wind speed from that same tornado outlet. Right. So this is Birmingham, Alabama. You can see at the surface here, the wind was 20 knots out of the south, and you get up to 500 millibars, and it's 70 knots out of the west. Right. Absolute perfect wind shear in those ingredients as it was set up. Okay. Question. Those are really broad ingredients. Okay. I'm going to come back on Tuesday and look at dry lines in a bit more detail, and then we'll get into the nuts and bolts of tomatoes and wool. All good. All good. All good. Okay. That's a little early.
Are you gonna go wash the bathrooms?
I have no idea what you're talking about. Yeah. Might catch a little bit of it. I do love the Masters.